Hello, everyone. Good
Hi.
morning. I hope you're all okay. Good morning in
You're
the
funny.
chat. So you are about to take the exam, and as always, you want to go into it with a positive attitude because a negative attitude won't help you any. so, um, yeah. Good morning. I hope you're all really doing well. I see everyone in the chat. Hi, Daniela, Nate, Mehmet, Rob, and Patricia. Everyone's here. Owen, hello, Jonathan, Amir, Saja, Isla, Andrea, Keon. Good morning to you all. Hi, Luis. Hi, Sanjita. Hello. Good morning, Luis. We have several Luises in the room. Hi. Um, okay, so um, good morning, Nathan. Any quick like logistical question before we start? Because
Is
might be able to start a few minutes early
is the unit for period seconds?
per second.
Per second. That's what I thought of.
Yeah. So that Randy is something you could look up in the textbook for like a quick answer. It's there. And remember, just physically, the definition of a period is a full cycle around, right? So one cycle per second or whatever it would be. Um,
So it's the same as like rate. So that the reason I was confused on it is because I thought angular speed was that. Is it the
yeah,
same
I,
as angular
I,
speed?
I don't want to go into it right now, Randy, because I might confuse someone else who already, you guys, we should start the test if there aren't any logistical questions. But I understand angular motion can definitely be confusing with the units, but period is per second.
Okay.
Yeah. Um, okay. Any logistical questions? We're good. Everyone has power at their house. Some people don't, unfortunately. So, um, yeah, let's just hope for the best. Okay, let me update the exam time so that the file is viewable. 10:02, and we'll give ourselves, 3 or so extra minutes, or 4 extra minutes. Oh yeah, it is crazy wind. Oh yeah, yeah. Yeah. Okay, guys. So I hear you guys, lots of things going on. So if anything happens, do your best to communicate with me as soon as possible, either through email, through private chat, but make sure to do it today. Make sure to do it today if anything happens. Okay, I'm updating the exam. And if you refresh your screen, it should be available to you now, and it'll be due at 11:05. So 2 extra minutes. Go, go, go. I'm going to mute everyone, including myself.
Professor?
Yeah.
In number 3, the angle of 30 degrees to the horizontal means 30 degrees above the horizontal plane, right? Or from
Yeah.
the... Okay, thank you.
Hi everyone. I have an announcement and I'd really like it if everyone could pay attention for the next minute. I'm going to put it in the chat too, but please kind of just stop what you're doing for a second. Great. I got somebody's attention. For number 3, you do not have to solve it. Just write the equation that you need to solve for number 3. Additionally, I'm going to add 10 minutes to the exam. Okay. So you'll have 10 more minutes. But for number 3, just solve for the variable, no numbers, and keep going on to numbers 4 and 5. So for number 3, I should be clear. I'm sorry. 3C. 3C. Yeah, if you solved it, great. But 3C is what I'm talking about. 3C. If you have an answer, that's okay. I'm only looking for how you solve for time in 3C. Okay. If you have any questions, chat it to me and I'll clear it up. I'll also put it in the chat right now. 10 extra minutes, so 11:15. Hi, everyone. You have just under 30 minutes until submission time. Hi, everyone. You have about 15 minutes left. Hi, everyone. You have under 10 minutes, so I would wrap up anything you're finishing and work on submitting your exam right now. 11:15.
Hi, I have a question real quick. When you ask for like part C, the equation, like, do you want us to put the equation, substitute in the numbers, and then say solve for or something, or do you like want the isolated?
Isolate the variable t.
Okay. And but then we solve for that number, or we just give the equation that equals that solve.
Just isolate for variable t and do nothing else.
Okay.
Hi, everyone. You have just about 2 minutes left to submit, so continue trying.
Oh, Professor, I submit the exam and I send it to you in both ways just to make sure everything is good. Thank you. Okay, everyone, the time to submit is done. So if you're still working on submitting, just keep working on it. The link will be open at least a few more minutes. Just keep going until you submit. Anything else, you could also email me as a backup. Um, just kind of work through it. And for everyone else who has submitted already, we have a break until 11:30. So take your break. Go and move. I'll see you all at 11:30. I'll
See you
continue.
then.
I'll continue working with people in the chat. Hi, everyone. I hope you're all back. And I also hope you took a minute to stretch, to move around. Hi, Isla. I'm glad you guys are back. Hi, Daniela. I see you too. Hello, Sanjita and Owen. Yeah, I hope you took a minute to stretch, wiggle around, and do whatever you need to do to get a little bit of energy. Hello, welcome back. um, yeah, hi, Mehmet. I see you all too. So it's Tuesday. We made it over our long weekend and straight into an exam. Isn't it funny? As much as you think you've prepared, the Monday morning rolls over to Tuesday morning after some after a long break, things happen. So yeah, I agree, Kian. The longest week of my life too. So I'll say, if anyone wants to discuss like individual problems with the exam, we can talk after class when it's just us and I'm not recording. There are some students out there that did not take to the exam for whatever reason. So I'd really appreciate it if amongst yourselves, you just don't talk about it just yet. Maybe if you know someone did take it, you can talk about it with each other, but in your group chats and stuff, just know that not everyone has taken the exam. The other thing, I know many of you, not many of you, but some of you were not able to see some of the markings on one of the questions for the exam. And I'm going to show you what it looks like, but I want you to know that it's okay, because the only markings I provided were just variables. There were no numbers. So to solve the problem, you would have had to have added your own angles anyways. So let me just show you what I'm talking about. So you see it, because some of you I know just didn't see it. And I could see it on your exam. So, just know that it's on my radar. I know if you have a drawing on there, I'm going to look at your drawing too. And I always grade based on what is your interpretation that's written on your exam. So there, this is the actual file with the preview, but for any reason, if someone didn't see it because of whatever program you used or whatever happened, it's okay. Because to solve this problem, you would have had to have placed your own angles. And if your numbers are used or your equation uses your angles, then it's okay. If you didn't see it, that was probably just maybe a minute or so extra that you would have liked to have had. And Owen has a question. If I change the subscripts on the thetas in my drawing, is that okay? Yeah, as long as that's what's reflected on your paper, and then it's on your equation, that's perfectly fine, right? Okay, so I just wanted to put that out there, that if you talk with people after the exam and realize that you didn't use the blue writing, that's okay, as long as whatever's on your paper is how I will grade it. Other than that, just so you guys know that these kind of, we're all human, so any little mistakes you found, things like that, it's okay, just kind of go through them. I usually write the solution for the exam completely. And the only problem I did not write the solution for this time was 3C. So I was in class when you guys were taking it, also writing it, and I was like, oh, this is this is gonna take a little bit longer. And so that's why I made the announcement to change things up. But thanks for going with the flow. I don't think the extra 10 minutes made a big difference for many of you, because I had about 75% of the submissions before the normal time, which is 11:05. So good work for that. So let's see. Overall, just keep practicing the homeworks, and we will keep getting better at all this. Okay, let me hear from you guys. Any comments, questions?
Are we going over motion of a system today? This week's module isn't up yet. Patricia, I actually just published it during the break. So if you hit refresh on Canvas, I hope you should be able to see it. It's right on, yay, okay. Okay, good. Yeah, so we are going over motion of a system today. We will have 3 chapters. Now, you might be worried because it's a shortened week, but these chapters are short. They're short and we can get them done. Yeah, so I wouldn't give you more than what you could handle either. The only other adjustment we're going to make for this week is that the lab and the lab only, the 2 labs that you'll have this week, are going to be due on Monday. You should finish them, or at least the work, and then, you know, you could do the rest of the lab over the weekend. But the actual writing, the actual maybe calculations or looking at the simulation, you should do that. Yeah. I have a question for me. Can you tell us what pyramid that was in the free body diagram lab assignment? Oh, that was the pyramid in Cancun. What's it called? Chichen Itza? I think Chichen Itza. Yeah. Yeah. Yeah, Daniel got it. Yeah, it is Chichen Itza. Yeah. Yeah, that was me. Yeah, that one. That's the one. That is yeah, that was me.
I think that exam was much easier than the, I don't know. I feel like the stuff I studied that I was having difficulty with wasn't on it. And so it seemed much more like simple.
All right. I'm glad you feel that way. And you know, when things are really complicated, that usually is a sign that we have to spend more time on it. So it might not be appropriate to put that on an exam that has to be done in 1 hour over Zoom, you know? So I will say that in my normal classes on campus, the exam is usually at least 10 questions for the same amount of time. And you shoot right through them. But in class, I can walk around and kind of help, you know? Yeah. Oh, do you think you could walk us through a problem on last week's homework? Yeah, and I could do that. It's probably best to do it after class, but I can do it. Yeah. Okay, so for this week, again, let us get started. We have a few minutes. The goal is to get through chapter 7 today. And then at the end, we're going to finish at 12:30 today, no matter what. I want you guys to read the lab before we talk about it. And I'll tell you a little bit more about that at the end of today. But yeah, if any more questions, feel free to put them in the chat, or ask. Sanjita says, should we be able to do the lab today? You probably can, but I'm not gonna assign it today. I'm just gonna tell you to read it today because it's long, that's why. So I think you should get ahead and read it. Not start it, but read it. Okay, I'm starting up my slideshow here, and I'm going to share it with you guys in just a second. So as I find this, I'm gonna be confused for like the whole week. I don't know what day it is, but I just have to keep reminding myself. Okay, we're all here. Okay, so what you see right now is the energy of a system, and this is chapter 7. And so what we've done before this is look at motion, describe motion using our kinematic equations, and now we know what are the causes of motion, right? The forces that are applied on some object, some system. Well, we want to get a much more complete picture of what's happening in physics. So in the example that you see on the screen, the picture that you see here, we could apply some force onto the sandpaper and move it back and forth,
and we get our outcome of the smooth wood. But we can describe that motion of the hand and the sandpaper with some velocity, some acceleration, some force that's applied to cause this motion. But in addition to the motion that we see and that we're applying, what else is happening in the system as we're sanding down our wood? Anyone out there?
Friction is going down.
Okay, I hear friction is going down. That's a part of the forces. Yeah.
Mass
What else
is
do you see out
decreasing.
there? What?
The mass is decreasing.
Oh yeah, mass is probably decreasing of the panel, right? And then Mehmet tells us what it is that we're actually feeling, right? So in addition to us applying a force to cause motion of the sandpaper, we start to feel heat. Yeah, and Daniel and Luis also mentioned it too. So we cannot describe the motion of heat with our kinematic equations just as we know them already. So we need to look at the full system beyond just motion, and how is this like transfer of motion happening, right? What else is caused? Is all the force we're using with our hand being transferred to just the motion? No, some of it is being transferred to heat, or if you're sanding, you also hear something, you also hear the roughness. So that type of heat that we see is a type of energy. And by describing the motion of a system with also the energy of a system, you get a much more complete picture of the physics of what's happening. So we apply this force to the sandpaper, and we can most definitely get the acceleration because its velocity is changing. We know there is friction, absolutely, between the sandpaper and the wood, and this friction is caused by the changes in motion, right, that we're applying here. So this is all mechanics, something that we can describe with our kinematic equations. But the next thing that we also feel is this warmth. And so to describe the warmth and the motion, we need to also include the study of energy. And we're going to learn, I think, next chapter about the conservation of energy. Now, I mentioned heat and warmth, but I also said the sound, right? There are many types of heat, many types of energy, not heat. There are many types of energy that you can account for in a system, right? You can account for chemical energy, electrical energy, nuclear energy, many types. And so our goal is to study them all, and we're going to see them all in chapter 8. And in this chapter, we're going to study one of the fundamental quantities of energy, which comes from motion, and that is called work. So work is the first type of energy that we will study. So let's look at the first intuition we get from work. Work is always going to have to do with motion and movement of something. So in mechanics, of course, or in mechanics, when you're moving something, the movement is caused by something in the environment. And so if we look at this eraser here, something in the environment, a hand, your hand, is going to apply a force onto this eraser, right? So as we apply a force onto this eraser, imagine that the magnitude of that force is equal. The only thing that's going to change is the direction to which you apply that force. And some of the directions will result in some displacement of the eraser. So which one of these images do you think will cause the least amount of motion, displacement?
Well, C.
Okay, I hear C, and I see lots of people say C also. I got one A, and I think we're, yes, that was a typo. Yeah, and it's C. And the reason you guys, maybe just physically, you put your finger on something, and as hard as you push down, you'll never get a horizontal movement. Here, the angle that's being applied with respect to this plane is 90 degrees. So that 90 degrees isn't telling us anything. Which one do you think is going to move the most? Which one is going to cause a horizontal displacement the most? Okay, I hear B, and I see lots of B's in the chat from everyone again. Very good. This one has the lowest angle, right? That lowest angle. And so you can see here, and you guys are correct. You guys are correct. The lowest angle here is going to cause more of a displacement. This lowest angle is also the largest value that will result for that X component. Let me show you what I mean mathematically. So everything that we've just seen based on, our physical examples here, we can now translate it to math. So if an object like the eraser undergoes any type of displacement along some straight line that is due to some force, because we applied a force on it, that force will make some angle theta with the direction of displacement. And so on the last slide, you saw the eraser being pushed down and it caused the forward movement. Well, you could also apply that force upward as if you were pulling a box with a rope or a chain and trying to drag it across the floor. You're applying a force, or a vacuum, right? A vacuum you have to pull across the floor. You apply some force at some angle theta that will cause some displacement. So that's everything we're doing. We're applying a force at some angle theta that will cause some displacement of the box. And so here, let me move around my screens. And so here then we have our definition, our formal definition of work. Work is going to be the displacement that you get by applying some force at some angle. So work is done by the force on a system. And work then is defined as, that's what this means, defined as the magnitude of the force times the displacement times cosine theta. And so this is all right now a magnitude. So if we look at, mathematically the product of these three things, it's kind of hard to picture how you come up with the product of all of this. What is the relationship that's going on here? When you think of the value of work, because when we derived force equals ma, we said you double the force, you can double the acceleration. There's a linear relationship here. But here, you're going to notice that when we apply a force at some angle theta, we are not considering the vertical component of the force. The thing that's giving us a value then is this f of x. And this f of x, we know, is the magnitude of f times cosine theta. So that's where this relationship comes from. F cosine theta comes from the x component of the magnitude of f. This is then multiplied by the displacement, and that product is called the work. Eventually, we'll learn that this is a type of energy of a system. So, what are the units that we're going to use here? What are the units and what is the direction? So this angle theta will always take care of the sign for us. If you end up moving an angle more than 90 degrees, your cosine theta will result in a negative value, and thus you will get a displacement, probably in, you won't have to get a displacement in the negative, but your work might be in the negative, which means that maybe instead of pulling, it was easier to bring it back towards you. Of pushing it, it was easier to pull. That's why your negative sign here will change the definition of things. Okay, so we look at our equation. W equals force times the displacement times cosine theta. If theta is equal to 0, which means that the magnitude of the force is already along the x-axis, now you've maximized that value of force. Cosine of 0, anyone?
1.
Yeah, cosine of 0 is equal to 1. And so we can maximize this value by pulling horizontally along. And we know physically this is true. If you pull directly, you will get the most displacement, but if you pull at some angle, you're not going to get as much displacement in the horizontal direction. So this cosine theta will always take care of the sign for you as to what is smaller or larger for the work. Cosine theta will take care of the sign for the value of work. Now our units are based on, the product of the variables here. So a force is Newton, the displacement is meters, and we don't have the angle for cosine theta because it'll result just in radians or in some displacement. So the unit for the work is the Newton meter. The Newton meter is what defines our joule. And so joule is probably what you've heard as the unit of energy. So this is a clue that work is going to take us into energy. So the SI unit is always going to be the joule. This breaks down to kilogram meter squared second squared, which is just the Newton meter. So if you forget, you can always break it down in terms of what you're given here. You could even break down the Newton and it'll all work out.
So the difference between this and a Newton is the meter squared?
Just 1 meter, just the meter.
Oh,
Uh-huh.
duh, because it says, okay.
Yeah. So the Newton, and again, the way that I remember this is F equals MA. I can't remember that the Newton is kilogram meter second squared. I remember mass and acceleration. And then I go from there because, yeah, I'm not good at remembering things. Okay, so let's try a directional question now. Okay, this figure shows 4 situations in which a force is applied to an object. In all 4 cases, the force has the same magnitude and displacement of the object. Oh, and the displacement of the object is to the right and of the same magnitude. Oy, I'm going to read this again. In all 4 cases, the force has the same magnitude. Okay. And the displacement of the object is to the right and of the same magnitude. Okay. Rank the situation in order of the work done by the force of the object, from the most positive to the most negative. So what they're saying is that this value for the force, the magnitude is the same for each problem. Then the displacement is always to the right for each problem. So notice that the arrows just are in the same direction. So given what we know, our equation, FR cosine theta, figure out then which one is the most positive and which one is the most negative. Which one is the most positive, everyone? The most positive.
B?
C.
Or wait, no, C.
Okay, I see. I heard a B and a C and changed back to C. And then I see some more C's. Okay, so let's look at C first. The angle here is 0 degrees, right? Because they're parallel to each other. If we look at B, the angle here, you can just make your axis, is that 180?
Yeah.
Yeah, this is 180. Okay, and now let's look at the angle here. It looks like 90 plus 45.
135.
Thank you. You guys know those are my faces. And then here, the angle is 90 degrees. So if the magnitude of the displacement and the force are the same, the only thing that'll vary is this cosine theta. All right, so we have some answers now. We'll go with what Mehmet tells us. CADB. So C will give us cosine 1. Cosine theta will equal 1. Oh man. So y'all will see how much I know how much I remember. This one, theta equals 180 will give us negative 1. This one will give us 0, I think. And this one will give us some negative value. I do not know the answer, but I know that the x component will be negative of f of x. And so I know cosine theta is negative there. So the answer, I think, is C, A, D, B. Yeah, Mehmet, that's totally right. Okay, and a question from Henry. I don't get how the displacement is to the right for some of these. That's a great question. And this is where our intuition comes into play. Now let's think, okay, think of the word work. right? Now, physically, we know it's going to mean energy, but think about when we're using the word work in real life. If it takes us a lot of effort to do work, that's going to be a positive number. If it's easy for us to do something and we don't have to put in a lot of effort, that's usually going to be a negative value of a work. So, for example, here you're going to have to pull a lot, right? Pull a lot to get that highest displacement, and you'll have to do some kind of work here. For this negative one, you're going to do no work, but your solution eventually will not give you the right displacement there. But this negative value of work will imply that you're not applying a force in the direction of displacement to cause that displacement. You're applying it in an opposite way, which is going to be no work, because you're not going to produce a displacement there.
How are you able to go to the right by applying a force to the left?
So you're not okay.
Is there something else going on that we're not seeing, or?
Yes, what's going on is work. It's not force. So don't confuse force and movement as what it is that we're measuring with work. How about we think of the best example that I like for the value of a negative work and a positive work is a piston and gas is contracting, right? So when you have to push down on something, you push down on something. What are those called? It's a piston, right? A piston. Okay,
yeah.
You're pushing down on a piston and you have a set amount of gas in there. The more you push down here and the harder it gets to push down, the more work you have to do. As the piston moves up and you just gently have to pull it up and the gas is allowed to expand, you're doing less and less work. And that is a negative work that you're doing. All it's conveying is the direction of what's happening and whether expansion or contraction is happening. And that would be your same situation here. If you're applying a force in the same direction, you're going to get a large displacement and you're going to do a lot of work. But if you apply the work in the opposite direction, you're not going to get the displacement that you want at all. So instead of—
How are you going to get displacement at all, though? That's what I'm like. If it's displacement to the right, how would we get that if we didn't put anything to the right?
Right. So physically, if you're not putting any energy into it, you're not going to get that work. Right? The conveyor belt that's on a horse. Okay. So again, we're not looking at the displacement here. We're looking at the amount of work that you're doing to do that. And physically, if you're applying negative work, then you're not applying any work to be able to move the object. Does that make sense in this situation?
Like when you say applying negative work, like, so you're pulling it in the left and then you're going in the right. That's what I'm looking at, like, say B, I'm seeing that picture and I'm trying to picture any situation in the world that would ever work like that.
Right.
Like, absent of like other conditions.
But you're thinking about the box's displacement and we're not focusing on that box's displacement. So let's say here, you're going to push this box, right? And here, then we could consider this perhaps a pull, but that pull isn't going to result in, of course, you know that pull isn't going to result in that displacement. So you're doing no work to cause a displacement.
So like all of these pictures are like the goal is delta R, but that is not what the actual is.
That's not what we're physically studying. What we're physically studying is the work. But the example is just to show you mathematically, how the angle changes things. And the angle is what will tell you if you're doing work on something, or the other way around, if something is doing work on you. And that'll be more.
Okay.
So this negative is really a point of view. So if we look at, for example, number B, like you said, I can never, ever pull so hard on an object that it'll cause it to go forward, right? So physically, I hear what you're saying. That's true. in this situation, that would be more and more negative work. We are going to do no work to push this forward ever. So work is the quantity, the quantity combination of force and displacement and angle and pushing something forward. How much motion are we allowed to have in something? Yeah. Okay, so those so B is pulling us. Yeah, it's almost like in B when it's negative, it's almost like the object is pulling you. That's a really like a horse. Yes. I hear you, Keon. Yeah, so the idea of work, the negative sign will always tell you the direction, the perspective that you're taking. Either you're doing for a gas compression and contracting, you're either doing work on the gas or the gas is doing work on you, right? Either the gas is pushing back up at you or you're pushing down on the gas. No, I know some bad jokes are gonna come right now. Let me move on to a problem. Yeah. When we say gases, I mean thermodynamics, people. Okay, let's try this problem. This one physically makes sense, so it shouldn't throw you too much for a loop. A man is cleaning a floor and he pulls a vacuum cleaner with a force of magnitude 50 newtons at an angle of 30 degrees with the horizontal. Calculate the work done by the force on the vacuum cleaner as the vacuum cleaner is displaced 3 meters to the right. Okay, so we have displacement 3 meters to the right. Notice how this is worded too. The work done by the force on the vacuum cleaner, right? What is the force done onto the vacuum cleaner? So we should expect something positive here.
So like 50 Newton cosine.
Yeah, we have our force, we have our angle, and we have our displacement. So we can calculate for this. Yeah, there we go. I heard you guys saying it and I see Owen putting it there. Yeah, and I think if you calculate that out, you should get around 130. I think that was just a calculator typo, Daniela. So our 50 newtons are 30 meters, and I'm sorry, our 3 meters and our cosine of 30 will give us 130 joules. That's how much work the man here is applying to the vacuum cleaner to move it. So notice what we're talking about is the physical energy that this man has to move something, right? Is W equals FD only when the angle is 0? Yeah, okay, so that's a really good point, Owen. So to maximize this work, you could also say work equals FR. Whenever they are perpendicular to each other, right? Whenever these, did I say perpendicular? Parallel. Whenever this force is parallel to some distance R, then theta is going to equal 0. And when theta is equal to 0, then you have your maximum horizontal component there. And so the max value for theta equals 0 will be F times R, or this R is the distance, so you can call it the letter D also, which is what Owen is referring to. So that works. But notice what we've done here, guys. When we're applying some force, this is the force, right? We're applying some force. We are saying that the largest part of the force that is going to cause the horizontal displacement is the horizontal component of the force. If we use the vertical component of the force, we are not going to have any horizontal displacement whatsoever. And so mathematically, you guys may have all seen this already before. Then our value of work is equal to this product, which mathematically is equal to an operation called the dot product or the scalar product. And this is where you can look at the vectors and have a result as a magnitude, a scalar value. So this is the force vector dotted with the displacement vector. And these two, oh my gosh, these two vectors will result in a scalar number. They will not result in a vector number. They will result in a scalar number, some value in joules. Work here is not a vector. Work here is not a vector. So this scalar product is also known as the dot product.
So doing like a dot product on things like that we had been doing would have given us the x, would have given us the vector rather than the x and y component.
If we do it,
Like if we use the dot product on the vector before, rather than breaking them into x and y components, we could have gotten the answer in the vector rather than the x and the y component.
You would have gotten the answer, but only in the x component. So I wouldn't, you're correct, but it's only in the x component. So I wouldn't look I wouldn't look to this as like a shortcut to it. Because here's why, because physically the dot product means something. I know that we're making this connection because mathematically FR cosine theta happens to be the x component of the force, but physically it's a projection of one component onto the other, and though the product of that projection is the value of work. So it's not a physical meaning, but it's like an intensity. Okay, so, and this is super important because in next week we're going to learn about the cross product, and mathematically you might already guess that the cross product will give us the vertical component, but the cross product physically is an upward motion. You can think about a bolt threading in and out, and the cross product physically gives us the direction of whether the bolt is going to thread up or thread down. So the dot product also is a physical component that we're measuring. But mathematically then we can just look at what the dot product is for any two vectors, not just the force and the radius. And so this is the dot product. A dot B is equal to the product of the magnitude of A times the magnitude of B times cosine theta. So AB cosine theta, the two vector magnitudes times cosine theta, is the dot product A dot B. So again, notice everything is parallel to each other, right? To get that maximum value. So only what's happening on the X. So let us look for, let's take the rules of the dot product. But let me see if I could just quickly survey you guys. For those of you who have taken classes beyond Calculus 1, have you seen the dot product already? Anyone out there? You have, but Randy, you just finished Calc 1, right?
Yeah, I saw it in pre-calculus. We did dot and cross product both.
Okay. So I've heard in the past that some people saw it in Calc 3 and Calc 2. Oh, okay, but you've seen, MATLAB, of course, you should see it there. But the prereq to MATLAB is also Calc 1. So, okay, so you guys have seen dot product. Maybe Oh, okay. So surface integral and using Green's theorem. Okay, this is great then. This I love the winter class because y'all are always super on top of it when it comes to math. Okay, so let me go through the rules and see if we could add something more to what you've learned about the dot product, maybe some physical meaning to it all. Okay, so A dot B is AB cosine theta. What is this in our vector form? We're taking the vector B. This could also be some sort of force. And we're going to project that vector B, and the projection is downwards. Project that vector B onto vector A. This could be something like your displacement, right? So when you project that, just that horizontal component, which is B cosine theta, and you multiply it times the magnitude of A, that projection coupled with the A vector gives you a magnitude for the amount of energy or work that you can do to actually displace an object or cause motion of some sort. So physically, that's what it is this B projected onto vector A. And so mathematically, we can do a lot here, right? So the first rule is that the vector, the dot product is commutative. So A dot B will equal B dot A. So AB cosine theta is the same as BA cosine theta.
So like initially was A like something else, like, or is that the final?
Um,
Like
um,
A and B, I see them both. Is A dot product B, that's equal to the AB cosine theta. Now, is that AB cosine theta, like, what is that? Like, where is that? Is that like that whole A line?
So here, let me underline them so we can define that. So B cosine theta is this here, which is the projection of
Oh,
B.
okay.
Uh-huh. And then the vector A, you might think is just that component, but it's not. It's the entire vector A. And that makes up A here. So it's the magnitude of each of those. And that product of those magnitudes is the amount of work that you can do on a system. Yeah, I hope it is helpful to Calc 3 stuff. And then I have a question, dot product cannot be commutative, I think. It can be, right? Because BA cosine theta will be the same as AB cosine theta. And you could also flip this around and still get the same value. I wonder if I have a proof for you. I think there might actually be one in the homework, but it is commutative. The cross product is not commutative, and that might be what you're thinking of. Yeah. Okay, this also follows the distributive law of multiplication. So we can distribute the A that's dotted onto with the sum of B plus C. This A will distribute out just like it would in multiplication. So this will become A dot B plus A dot C. And then just because of the definition of the dot product, we can make some straight rules, right? If A and B are perpendicular to each other, this means that theta is equal to 90 degrees. And if A and B are perpendicular, this means that A dot B will always equal 0. No math needed. And then we know the other way around, if A and B are parallel to each other, and we know theta is equal to 0, that means that this B vector is already on the horizontal parallel to A, and so we can maximize that value. Theta is equal to 0. So A dot B equal the magnitude of AB, because this cosine theta will equal 1. And then finally, if A is parallel to B, but in the opposite direction, right, we will get that negative AB value because cosine theta will equal negative 1. So doing this, we know that we're actually working with vectors. And of course, vectors are written in their unit notation with I hat, j hat, and k hat. Now, when we multiply and distribute a vector out and distribute its components out, we can apply the dot product to the actual unit vector itself, and we can figure things out. So we can use these major rules to help us with the unit vectors, and I'll show you what that looks like on the next slide. Okay, so if we wanted to look at our unit vectors, we remember that the unit vector is you could give it a value of 1, but it doesn't have any dimension. It's only there to give us direction. So the unit vector I, j, and k follow the standard axis of x, y, and z. And so we can break these down and multiply do the dot product for the unit vectors. So anytime that I is dotted with I, or j is dotted with j, or k is dotted with k, we know that they're parallel with each other. So cosine theta will equal 1, right? So this value will always equal 1. And this is theta equals 0, meaning cosine theta equals 1. And anytime that a unit vector is dotted with any other unit vector, like I dot j, and it's 90 degrees, or I dotted with k, and that's 90 degrees, or j dotted with k, that's my best one. That's my best perpendicular angle. Then this will be theta equals 90, and this means cosine theta equals 0. Yeah, Owen says it's like they're out of phase or something. That's exactly right. That's a really good way of thinking of scalar products and dot products. Dot products will give us that horizontal motion or parallel motion, and then later the cross product will give us that vertical motion. Yeah, so we're looking at what's in line in the horizontal. Let me put my timer on and let us actually see what this looks like in math form then. So let's say you have your two vectors, right? Vector A expressed in unit vector form. So again, the component, direction, component and direction here, and vector B. Now, if we wanted to dot them, we would distribute all of the components out with each other. So the component, the dot product of A dot B then would be AX times BX times I dotted with I. That's not an arrow, that's an I. Maybe I'll make it like that. That's an I. Yeah, yeah, I, K, not, oh my gosh. Oh my gosh. I, J, K, I, J, K. I think it's right, Nathan. I'm not sure unless I
He's
wrote
talking
it.
about on the top. He's talking about on the top right, I think. It says IJ, IK.
Oh, yes. Thank you, Keon. Thank you, Bradley. Thank you, Nathan. I dot J. What should this other one have been? J dot I, perhaps. Oh no, I dot K. I dot K. Thank you, guys. And I'm so happy you caught that because I don't think I've ever seen this typo. Yeah, I dot K. Perfect. Oh, I did it here, but it didn't match what I was saying. Yeah. Okay, so let's do this math then. So we're doing A dot B. So it's just like multiplication because it follows that distributive law. So we distribute every component. Magnitude of something times the magnitude of something is just a scalar product. And then we have the two vectors. Those vectors have to be dotted. So I dot I is equal to 1. And that's why you don't see any value there. If we then we distribute this out, right? We distribute it here, and now we distribute it there. You would have AX, BY, I hat dotted with J hat. And here we see that I dot J is equal to 0. I dot J is equal to 0 because they're perpendicular. So this value goes to 0. So anything that's dotted,
They taught us like a shortcut for this. Like we got this like derivation, and then like it was like this times that. It, like you added something else, but you didn't like pay attention to the 0 anymore.
Yeah,
there was like a formula to it.
Anything that's dotted perpendicular to a direction, anything that's dotted with a perpendicular vector is always going to be 0. So it's really nice to see for the dot product, AX, BX is the magnitude, the components along the same direction are the actual values that you're going to use. And so if you were to dot a vector with itself, A dot A would be AX times AX, which is equal to AX squared, right? Or AY times AY. Every other component that's multiplied with a component in a different direction will yield a zero, because the dot product is going to be 0. So this is what you want to remember. It's also really nice. The dot product is nice. The cross product takes more work, but yeah. Let's try some numbers in this, and we'll try it with just vectors, and then we'll try it with some actual forces and displacements. Okay, here's a problem. Vectors A and B are given by these vectors here. Determine the scalar product A dot B. So if you're really comfortable with this, go ahead and multiply to your heart's content. If you're not, do it step by step. And this is what it looks like step by step. So A dot B is vector A dotted with vector B. And now we're going to distribute each one. So 2I hat times negative I hat, right? 2I hat times negative I hat. Yeah, this is really cool. This is really nice. Okay, let's distribute the next one. That's this one. Now let's go 2i hat times 2j hat, and then 3j hat times negative I hat. So notice the negative comes out. And notice we keep the order j dot I exactly as you distribute it. And then 3j plus times 2j. So quickly you can say j dot j and I dot I are equal to 1. So those will stay. And everything else goes to 0. 0 and 0. And again, they go to 0 because...
Why is the 2 not negative in the bottom?
Which one? Here?
Yeah.
There, now it's negative.
Oh.
So in this equation here, I dot j goes to 0 because I dot j equals 0, and then j dot I is equal 0. So those just go to 0 as you see here. And now we have with our negative 2, thank you for catching that, our negative 2 plus 6 is equal to 4. And so the vector scalar product is equal to 4 here. And I see a question. So it's 4 times 0 because the axes are perpendicular and cosine 90 is 0. Henry, that's exactly correct. And that's a full formal definition of why that is 0. Because the dot product is looking for things along the same side, along the same component. And so if they're perpendicular to each other, they will not yield anything along the same direction.
So, and it's like first and last for this because the two middles end up being the perpendicular, which are 0?
Yes, in this situation, yes. But remember, you could also have like a vector with 3, but in this situation, you're right. So the way I would remember it is just all the like variables, all the like unit vectors go together.
Okay.
Yeah. So you want to get to a point where you're comfortable to jumping to this and just saying 2 times negative 1 is negative 2, and 3 times 2 is positive 6, and this equals 4. But take your time with it. Take your time with it. Okay. Let's try. What did I do here? Oh, that was the shortcut, right? Well, kind of a shortcut. Oh my God. Anyways, A dot B, you could just jump right to the components and it'll give you the exact same answer, which is what we just did. There's a negative that goes in. Okay. Now it says find the angle theta between A and B. So let us just remember that this A dot B is our equation. And this can be manipulated any which way you need to solve for that angle, right? And so cosine theta is right here. So you want to bring this AB down to this side and solve for this equation. Now to do this, you're going to need the dot product and the magnitude of A and the magnitude of B to solve for cosine theta. And a question from Nate. So direction variables multiplied by each other equal 1 when it's the same direction. That's correct, Nate. And 0 when it's 2 different directions. That's correct. If they're perpendicular, that's right. Okay, so to solve for this, you're going to need the dot product of A dot B, right? And divided by the magnitude of A times, oh hell, times the magnitude of B. This is just A and B. Notice there's no vectors on there. And this whole thing equals cosine theta. And that'll give us our angle theta. So let's get the magnitude of A and the magnitude of B because we know the dot product from the last one. And you guys know how to find the magnitude here. The magnitude of A is the sum of the square of the components, square rooted. And so you get 13. And then for B, the same thing. This should be bolded. Or no, this one should not be bolded. Magnitudes. And so the magnitude of vector B then, again, the square root of the sum of the squares of X and Y. And so now we can just solve using our equation for the dot product. And A dot B was 4, which we found on the last slide. And the magnitude of A times B is root 13 and root 5. And now we can get that angle theta. So you can manipulate this definition as, just that. It's a definition of an equation. So you can solve for it. Okay, I think we have time to finish this next problem. Let's try it. A particle is moving in the xy plane and it undergoes a displacement given by the displacement vector in meters as a constant force, and as a constant force acts on the particle, and the force vector is given to us in newtons. So here's the displacement vector, and here's the force vector, and it acts on the particle. Calculate the work done by the force on the particle. Okay, great. So we know the work is equal to F dot dr. And we know to use this equation, F dot dr, because we are given the force and displacement in vectors. Okay. We don't have any angle between them, right? So we just take the dot product of F dot dr, the force vector dotted with the displacement vector, and you can write the whole thing out, right? 5i hat times 2i hat, that's here. And then 5i hat times 3j hat, that's here. And then you can actually, you continue that, and now you can actually do the dot product, right? 5 times 2 is 10, and I dotted with I is equal to 1, so you get the value 10.
In this problem is the force being applied then in the direction? That's why they're parallel and there's no theta?
No, there's no theta because they're given to us just in vector notation. But what you said in the beginning was correct, that the force is being applied along the displacement direction. So our value of work is going to be positive here. The reason they didn't give us theta was just because they're using vector notation. That's the only reason. Not, yeah.
Oh.
Yeah. But could you draw this vector out? Yeah, you could.
Okay.
But had they given us theta, you could find the magnitude of F and R and just use FR theta.
And then, so we'd have to add them together?
No, add what together?
Like we'd have to add the force and then the, oh, never mind, they're two different things.
So here you have two ways of using the work equation, right? You have work in terms of vector notation, and notice that the work is a magnitude, and it results in a scalar, which is why it's called the scalar product, right? The scalar product of two vectors is just a number. Or you can find it all in magnitude form, which would be FR cosine theta. So depending on what you're given in the problem, you can pick one from there. Okay, this is a good stopping point. Any questions about this? So again, just notice I dot j goes to 0, j dot I goes to 0, and j dot j will equal 1. And so we can keep that number here. Any questions about this? Again, the work is it's going to be a quantity of energy. So what is your capacity to do this work? That's what that value is telling you. Okay, I see and hear no questions, so I'll come back to you guys. Oh, Nathan says negative work is good. It can be good. If you're the one that's pushing and pulling, then you want negative work, which means that you're not going to apply a lot of work, and the thing is applying the work back at you instead of you applying the work on the object. Yeah, it can be good.
So like negative work, that might be like, say, an electric vehicle, like if it's doing like the regenerative braking, like it's getting work from the work it's already done at that point. Like it's getting energy because you're moving forward and now it's slowing it down, it's collecting it again, or?
I think that's a different type of energy that you're bringing up, which could still be positive.
Would it be like a person pushing a wheelchair for another person?
imagine like you're going up a hill, right? And you're pushing the wheelchair. You're doing work.
Yeah.
Now imagine the wheelchair starts coming back at you. Now
That's
you're
me.
doing, yes, now you are doing negative work, but the wheelchair is doing
It's doing
positive
work.
work on you. Yeah.
Oh, okay, yeah.
Yeah.
And so
Maybe
it's a
that's,
perspective thing too. Like the person in the wheelchair is having negative work on the way up the hill, and
that's
you
right.
are having, and then so on the way down they're having negative work.
Yeah. So when you're applying work to the wheelchair going up the hill, the work on the wheelchair that you're applying is positive, but the wheelchair is doing negative work because the wheelchair is not doing anything. You're applying work onto the wheelchair. Wheelchair? Yeah. Now I don't know what words mean, but
That happens. You say it too many times.
I have a comment, and for me, an interesting concept came up when I was studying for physics. It kind of relates to energy. It's about cooking a chicken. It does not relate to our topics except energy and work, I think. I have the link. Oh yeah, I'd love to see it, because any way that you could explain, oh, I see it. Any way that you could explain work, oh, I hope it's not a video. Any way that you can explain work is good. You're, I think the example of the wheelchair up the hill is really good, but if you make it flat, it's harder to grasp that. Also, work with the piston and the glass, right? If you push down on the piston, you're doing work. If the piston pushes back up on you, you are doing negative work because the piston's just coming up.
So like if
okay.
you're on a, so if you're like on a flat plane with that wheelchair, you push it forward 10 feet, right? You've done work. Now you pull it back 5 feet. You've still done work, but you've done positive work and negative work. And so your work is still positive, but it's half of that. So it's 5. Like your displacement is 5. So your work is half of what your original work was.
Are you looking at like I think you're looking at like the full like back
Yeah,
and
like,
forth.
yeah. Rather, because
Yeah.
like if you started the problem only when you turned around, then your work would still be positive depending on how you're looking at what your intention was.
Yeah.
Okay.
If you're looking back and forth, then yes, you would be adding a positive and a negative. And Daniela brings up a great point. If you look up Stirling engines, this can help visualize this. Yeah. Oh, there's a cat. Yeah, a Stirling engine will show you the concept of contracting and contracting gases and expanding gases, and the work that's done on the object or the piston that is moving because of the gas contracting or contracting or expanding. Now, I'm really happy you guys are into this, and I go for it. But at the heart of it, in Physics 101, you really want to make sure you get the math part of it right. Well, we're going to do a lot of work in Physics 102. Okay, I want to stop lecture here, and all I want you guys to do for today, of course, if you could start reading the chapter, look at the homework, you have the ability to start at least a few of them. I want everyone to read the lab. The lab is long and has a lot of components. I want you to read it. I'm not saying that you'll be able to do it or understand it right now, but I just want you to read it fully through once in case any questions comes up, and then we'll go through it in detail tomorrow. Tomorrow we'll finish chapter 7. We're only like maybe 4 or 5 slides away from finishing, and then we'll also start and finish chapter 8. It's not very much, so I think we'll be okay.
So you said tomorrow we're gonna finish chapter 8.
Let me just say we're totally done, but I'm gonna stay. I'll keep recording for a little bit longer, but if you want to go, you can go. But I'll still be here. Yeah. So yes,
Thank you,
tomorrow
Professor.
yeah, no problem. Bye, Kiana. So yes, Randy, tomorrow we are gonna finish chapter 8. I'm pretty sure we'll get there. Bye to everyone else in the chat.
And then are we doing chapter 9 after that or no?
We'll do chapter 9 on Thursday, and it's going to be very short also. But again, enough time to do things. Oh, and Owen had a question. Yeah, let me start arranging my windows. See you tomorrow, guys. Bye, everyone. I'm so sorry I'm not able to say individually goodbyes. Let me
Yeah.
move things around.
Same. I have that question too.
Oh, okay. Let me.
The last part,
okay.
especially.
Okay, let me hold on. I have to talk to someone else. Okay, let me see if I can look at number 40 really quick, and then I also have to talk to some people. So we'll do both of those. Thank you, guys.